In the last video, we followed Einstein's search for gravity. We saw how general relativity transformed gravity from a force into the geometry of spacetime. We saw starlight bend during a solar eclipse. And we saw how Carl Schwarzschild discovered something hidden inside Einstein's equations. An object so dense that even light cannot escape. A black hole. Black holes create an obvious problem. They don't emit light. Light cannot escape. So how do you study something that cannot be seen? If two black holes collide, there may be almost nothing for a telescope to observe. It seemed possible that some of the most dramatic events in the universe could remain hidden forever. General relativity had transformed gravity into the geometry of spacetime. But that raised a new question. What happens when that geometry changes? Imagine a black hole sitting perfectly still. It creates a stable distortion in spacetime. But now imagine it starts moving. The distortion changes too. Now imagine two black holes orbiting one another. The geometry around them is constantly changing. What happens to those changes? Einstein's equations predicted something remarkable. The changes spread outward through the universe, as ripples in spacetime itself. Gravitational waves. At first, gravitational waves seemed like an obscure prediction. But scientists soon realized they could become something much more important. For centuries, astronomy depended on light. Visible light, radio waves, infrared, X-rays. But gravitational waves could reveal events that light never could. It would be an entirely new way to observe the universe. For decades, nobody knew whether gravitational waves could ever be detected directly. But in the 1970s, astronomers found strong evidence that they were real. Russell Hulse and Joseph Taylor discovered two dead stars orbiting one another. The orbit changed over time, exactly the way Einstein's theory predicted. Scientists now faced an enormous challenge. If gravitational waves were real, could they ever be measured directly? The answer seemed impossible. By the time a gravitational wave reaches Earth, the distortion is unbelievably small, roughly 1,000th the diameter of a proton. Yet scientists decided to try. For decades, engineers and physicists built one of the most sensitive scientific instruments ever created, the Laser Interferometer Gravitational Wave Observatory. LIGO. Many scientists devoted their careers to the project. Among them were Weiss, Kip Thorne, and Ronald Drever. For decades, they pursued an experiment many believed would never succeed. LIGO uses a laser. The beam is split into two identical paths. Each path travels down a 4-kilometer arm. The light reflects from mirrors and returns. If both arms remain exactly the same length, the light cancels itself out. But if a gravitational wave stretches one arm and shrinks the other, the cancellation breaks. A signal appears. Then on September 14, 2015, it happened. A signal appeared. For a fraction of a second, space-time itself had moved. The signal came from two black holes, one about 36 times the mass of the Sun, the other about 29 times. For millions of years they orbited one another. Then they spiraled inward, faster and faster, until they merged. Detecting gravitational waves did more than confirm Einstein's theory. It gave humanity a completely new way to study the universe. For the first time, we could observe events that might be invisible to ordinary telescopes. We were no longer limited to light alone. And discoveries came quickly. In 2017, scientists detected two neutron stars colliding. This time, astronomers detected both gravitational waves and light from the same event. The observations helped explain where many of the universe's heavy elements are created, including gold. For centuries, astronomy depended on light. Now humanity had something new. We could listen to the universe. What began as an equation in Einstein's notebook became an entirely new branch of science. But one mystery remains. What actually happens inside a black hole? And why does general relativity refuse to fit together with quantum mechanics?